Okay, so I'm going to share the screen. All right, so now we're going to go back to the problem, right? We're going to create the data set. We're going to call it transformed CIFAR10 training and transformed CIFAR10 test. And we're going to basically read in the data from the beginning and show you how we can apply at least 2 transforms all at once. The sequence matters in which you put them in, and you could add more transforms if you wish to do so. Where would these come from? From here, right? So these are the transforms that are available. So we're basically processing our data through these transforms. Okay, so let's go ahead and continue. So I'm going to create the first one. It's called transformed CIFAR10 training. Or let's use train to be more consistent. So I'm creating new variables here. So transform CIFAR10 train. So I'm going to call data sets dot CIFAR10. Then I'm going to do data path. Comma. This is going to be train equal true, comma. We're going to say download equal what? False, right? Because we already have it. Take advantage of that. And now here, we're going to invoke transform, the parameter we've seen before, equal transforms dot compose. And this is what allows you basically to like pipe different transformations to the data set, and it'll apply to all of them at once. So for instance, now we do compose, right? So we can move this one down. So then we can do this. Okay. Like that, right? And so now we just need to list our individual transformations that we want to do. So actually, maybe I should do this more consistently like this and like that. Okay, and so now it added something, sorry. Get rid of this one because we already closed it at the bottom, okay? So then in here, you can add as many transformations as you want. So the first one would be from transforms dot to tensor. Remember, what this will do is it'll take the images and convert them to a torch tensor. Then the next one we might want to do is transforms dot normalize. And normalize, remember, does something like this. So I'll do it up here. Normalize does something like this. Pixel equal pixel minus, this should be parentheses. So pixel minus mean divided by standard depth deviation. Do you guys see that? And pixel just means for every image, right? Now, the one thing that we need to make sure that we do is that we don't want to mix R, G, and B. So the reds are one thing, the blues are one thing, the greens are one thing. Got it? This is every pixel in every image that is 32 by 32 of all the 50,000 images. Got it? So where do these values come from? Mean and standard deviation. Do we already actually have them? We do, right? Where are they? They are in the view 1 and mean and view 1 standard deviation. We already have those values. We have 3 because we have 3 channels, and we apply this equation 3 times to each of the channels. For all the pixels then get applied this operation. Got it? So again, this is where Torch handles this. In the function, we can just plug in, what were the names? View1 mean and view1 standard deviation. Yep, just like that. Then we can repeat this same thing. And of course, you could add more. And I encourage you to play with this, add more transformations from the list to see what happens. Okay. But I'll just add these two. Remove this parentheses that I added here. Like that. Okay, so now I'm going to go ahead and copy this one. Right? I'm going to change it. So it's going to be transform CIFAR10 test. It's going to be data set CIFAR10 data path. Train here will be false. Download will be false. Transform will be equal to transforms compose to tensor and normalize. The same idea. Got it? Any questions? Now, if you notice, we calculated these from the train set. And this is the test set, right? Not the train set. So should we get the mean and the standard deviation from the test set instead of from the train set? What do you think? Right. So what I mean is the mean and the standard, we're using the mean and standard deviation here and here, right? But this one is the train set. This one is the test set, right? We got these from the train set, right? So does that mean that we should get these from the test set? Or can we just use the ones that we computed from the train set? Why? Huh? Okay. I'm not saying it's not like this, but I'm just asking why this is fine. Well, think of it in a competition. You wouldn't have access to the test set, right? Another thing is the 10,000 and the 50,000 in theory come from the same population, right? So you calculated a mean and the standard deviation from the train set, it should be valid for the test set because it's all the same data set. Do you see that? So it's kind of it was just FYI, but it's just something to think about, okay? This is okay. Because again, just think of this, you would not have access to the test set in a competition, only the train set. Okay. All right. So anyway, let's go ahead. So we have our data sets now. What else do we need to build? We will need to create data loader. Okay. We are also going to need to process the labels as well for the data loader to be able to take them in. So the way that works is so the labels are currently numbers, right? I think they're numbers. So then we can do here CIFAR, let's say CIFAR10 final, let's say, is going to be equal to, we're going to iterate through that transform data set. So we're going to do for img comma label in transformed CIFAR10 train. Okay, just like that. And for some reason, it needs these values to be in a tuple. So that's the only thing that I'm adding here. If you notice, I'm doing this. Okay, so it's a list of tuples basically that it's expecting. Does that make sense, guys? Okay, so I'm doing here IMG, which is a torch tensor, and label, which should just be a number. I think it is a number. Okay, and then I'm going to repeat this process for the test. So let's run this one. Oh, and let's put, yeah, this is fine.
You never ran, sorry.
Did I not do that? Oh, okay. Okay. Okay, so let's do that one. Okay, it worked. So now let's try this one. Okay, great. And now we're going to repeat it for the other one. So let's add a few more cells. Let's go in here. Oh, I should have called this one train. So I'll need to run it again. Sorry. All right, let's start typing the code for this part, which actually should be similar. Okay, it's taking a while. All right. Hmm?
Oh, yeah, you said the test.
Yep, I need to change this, right? All right, so let's kind of look it over again. We're almost done with the data set, hopefully. All right, so for IMG label in transform CIFAR10 train, and all we're doing is creating a list of tuples, but this is already a torch tensor, which is an advantage, okay? And we got our label, which should just be a number, I think. So that should be fine. Then here for IMG label in transform CIFAR10 test, and we're going to assign it to CIFAR10 final test, okay? So let's run these two again, okay? As you can see, whenever we use for loops, it becomes slower than whenever we process things as a torch tensor. And then this is now finally data loader. Okay. All right, while it's processing, we can create the train data loader, which this is exactly what we use, how we did in regression. We created a data loader as well. Here we're going to say what? Torch dot utils dot data loader. And we're going to read into it CIFAR10 final train, comma. Now, what else do we specify in the data loaders? We specify the batch size, which will be what? 32. An important thing to consider here is memory, your RAM on your laptop, okay? So you may have to do 8. I don't know. But yeah, let's go with Lenny's. Let's see if Lenny is correct. So let's do 32. And let's see what's the impact on this. Remember, we got 10 labels. Okay, so we got to think about that, right? That's what we're trying to predict. Okay, great. So what else do we do in here besides the batch size?
Learning rate or
not learning rate. Shuffle. What is shuffle? Every epoch, all the data gets randomized. So all 50,000, one epoch, randomized. Next epoch, randomized, and so on. Got it? We'll shuffle equal true, yeah. Okay, so hopefully this will work. So let's go ahead and run it. Notice how that was pretty quick. All right, and our data loader should be done. So hopefully the train set is ready, and now we can proceed to build the network. I will only build a couple of networks. But we got to think about this a little bit. So what is the dimension of our data set? We read data sets. They're 3 by 32. Do you see what I'm saying? So now that we're going to start thinking about the architecture of the model, we need to know what the size of the input vector is. Do you guys see that? We're going to be feeding it 64 batches, which means 64 images, but each image is 3 by 32 by 32, right? And we got to think about the shape that we currently have in data loader, for instance. Okay, so here, what's a good place to look at this? Can we print the shape of this, for instance? Let's print the shape of this. Print dot shape. Let's see what happens. All right, so CIFAR10 has no attribute shape here. Okay. So then we can do this one here. So let's take CIFAR train. Should have done it in another cell. I'm trying to determine the shape of this.
Actually,
Yeah, go ahead.
There is like one page.
Mhm.
They have like dot data dot shape.
Dot data dot shape. Okay, what did it give you?
10,032.
10,032, 32.3. Okay. So you see the problem, right? We're going to need to figure out how to take that and put it into the neural network. We'll probably have to use view for this. Okay, so we're going to leave the images as they are. Oh yeah, there's a tuple in here too, huh? That's right. Let's just do what you recommended, actually. I think your solution is probably good. What was it? Just this one? So dot data, dot shape?
Yeah.
Okay. Right, so this is what I was getting at. So the images are currently 32 by 32 by 3. So it's, if you ignore this part, whenever you get something from this, you have a cube. And we got to connect that cube to the neural network. Got it? So we're going to need to, at some point, to spaghettify it or something so that it feeds into the neural net. Okay, so what is 32 by 32 by 3? What number is that? What number is that? 32 by 30, huh? 3072. Okay. So if I have a batch of 64 images and they're 32 by 32 by 3, that means that I have 64 images of 32 by 32 by 3 that if I spaghettify them, now they're a vector of 3072. So the simplest thing when you're building something like this is to take this approach and have that be the size of the input vector to your neural network. Do you see what I'm saying, guys? In the future with CNNs, we take a different approach. It's almost like you leave it as a cube. But here, because of how we're doing things, we're gonna stretch the 32 by 32 by 3 Rubik's Cube into one vector, okay, of size 3072. Got it? Okay, so let's build an architecture for that. So I have that number is what I was looking for, to know where to start in the architecture. So I'm going to go ahead and now build my first architecture. I'll run all these just in case, because I kind of think I messed up some of this. Okay, while that's happening, we can start building the architecture. So let's call this architectures. Okay, hit run. All right, so now remember, I'm not going to use the object-oriented approach that I did in the previous ones, because that will be your homework assignment. I'm just going to create it kind of like very simple way, but I will want you guys to change it into that. Do you know what I mean? Like when I say the object-oriented approach was, we did something like define, MLP, yeah, and then you did like init, and then you did the forward, right? Remember that? That's what's going to be homework for you, to convert what I'm doing into that format. Does that make sense? Okay. That's, you know, that's one of the consistent things in this class that I want to keep, is for us to always write things in that way. All right, but I'll write it like this, in not in an object-oriented approach. So let's do the first architecture. Let's call it model MLP. If I say MLP, what does that mean? And what is the architecture of this? Input, one hidden layer, and an output. It's still a neural network, but it's not a deep learning algorithm, technically. Exactly. All right, so then I'm going to do, now I need my NN module. So for that, I think I haven't done this part, so let's add that library to the top. Okay, so let's add it here. We're going to say import torch.optim as optim. Notice these are the same things we used before. And we're going to import torch.nn as nn. Okay. Hit run. That's available now. So now we can create our architecture. So I'm going to show you a different way, which is to do this, nn.sequential. Okay, just like that. And we can build the architecture. Just remember, you will need to convert these you need to convert these to object-oriented format. Okay? But that will be, I leave that to you guys as homework. Should be pretty straightforward. All right, so now the approach is similar, right? We need to build an architecture. So the way that we build it is nn dot linear. Then we can do, you know, like nn dot linear, and you can add as many of these as you want. What else do you need in here? You need activation functions, right? So nn dot relu, for instance, for tangent. All right, so you guys help me out. So how do I build this now? We need to provide the dimensions, right? So what are the dimensions here? It's an MLP, so we know some things about. So linear what? What's the input size? The input size goes here. What is that value? It's not 10. At the beginning, no. Not 50,000. That this is the, what is that number?
That's like the size of each.
The size of each image, yeah.
So would that be, so would it be that times the 50,000, or would it just be the 37?
So that's a good question, right? So the way that these frameworks are built, they work whether you give it one image, a batch of 64 images, or all 50,000 images if you had enough memory. So it doesn't actually care about that parameter. You don't have to define it anyway in the architecture of the network. What you have to define is the size of the image itself, whether it's 1, 64, or 50,000. So that's what goes in input. Got it? So then what is it? 3072, right? Which is what? 32 by 32 by 3. That's why we just did it right over here. So that's the input. Does that make sense, guys? Yeah, this is how it starts. Now, keep in mind, our data loader does not have 50,000 images of vector 3072. It has 50,000 images of 32 by 32 by 3. So we have a discrepancy there between what we have in the data loader and what the architecture is expecting, which means we can fix it, but we need to do it somewhere in between. Got it? So we need to do that, okay? So 30 by 72. Then let's imagine we're at the last layer. So the last layer would have also something like this, right? Okay, what is this value here? This is the last layer. This is 10 because we have 10 classes. Got it? All right, so now it's an MLP. So what do we need to do? 8? What is 8?
The function for the function to activate that.
The activation function, 8?
I think she's saying the size of the, the size of the number of
Oh, the number of neurons you mean here, right? Yeah, we need, let's not have a value yet. Let's just put question marks in. So this is 3072 by something. The hidden layer is something. What else? What value would go here then? It's an MLP. The question marks, right? The question marks. We haven't defined it, but the architecture only has one input layer, one hidden layer, one output layer. Do you guys see that? Then we have an activation function. Does it have to be ReLU? I mean, it could be something called tan H, sigmoid, etc. Okay, so there are there's various activation functions. We can go with ReLU for now. So now we know it's 30 by 72. This is 10. So what value should this be? 5,000. Why? So you're giving it more neurons than even what the input has. The input has 72 neurons. So here is where I think in the past I told you people funnel the layers. So that means that the next layer would have less, actually, not more. So for instance, it could be like 500. I'll use 512, but it can be any number. It could be 500, for instance. And okay, so if I did that, what is this value here? 510. Very good. Do you see that, guys? That's it. As far as that part, there's only one last little bit. So when we did this, we were predicting continuous numbers, right? Which means we were predicting like temperature like 32 or 78 degrees or 80 degrees, continuous numbers. But this is a classification problem. We're not going to predict continuous numbers anymore. Instead, we predict almost discrete numbers. Do you see that? We're going to predict 10, a vector. This vector is of size 10 for the classes. But we really, when we give it the data to a sample, so let's think of it like this. When we give it an image, we have a label 3, right? But this predicts a vector of size 10, right, guys? So we need to find a way to represent 3, this is the label 3, as a vector of size 10. So this needs to be a vector of size 10. This is called, there's a name for this, it's called one-hot encoding. You guys see that? So what that means is we have basically like an array of 10 cells, right? Where it's going to be, because it's an array or a vector, it starts at 0 and ends at 9, right? And we just need to convert the 3 into a representation that is of like this. So the best way to understand this is probably with an example. So I'll do like a few. So if it's 2, then the one-hot encoded vector should look like 0, 0. Yeah, 1, right? 0, 0, 0, 0, 0, 0, 0. Do you see that? Got it? Why do we do this? Because the neural network predicts a vector of size 10. That's how it's built. That's the architecture. We're building it to predict vectors of size 10. So then when we give it the training data, we have to give it like this. Let's do another one. Let's say I do 7. So I'm just going to copy this one, make it easier. So this is 7. So what does that mean? This one for sure is 0 now, right? How do I one-hot encode this as 7? This one, right, is a 1. You guys see that? Did I miss something? Yeah. Am I?
Yeah,
Really? Oh. Wait a minute. All right, so this would be 0, 1. Let's see. Class 1 says 1. Classes go from 1 to 10, I think. So 1, 2, or if it goes from 0, it's 0, 1, 2. That's how we were doing it. And then this is 0, 1, 2, 3, 4, 5. Oh, yeah. 7, 8, 9, because it starts at 0, so there's 10. Got it? I'll do one more, just one more. Let's say I'm going to do, you only have to do this for the 10 classes, so I'm going to do 4. So that means this is 0, And this is 0, 1, 2, 3, 4. So this should be a 1. Got it? So this is called one-hot encoding, and it's happening because the neural network is going to predict 10 classes, basically. So it's going to predict vectors where everything's a 0, and there's going to be a 1 on the position that it selects as the class. Okay? What works about this is that then this is the real data, right? This is the real data. And then we are building, we need a machine. We need a machine that also produces vectors of size 10. Okay? So we need to force it to predict what? Only zeros or ones here and nothing else. Do you see that? There's that additional little trick. If we don't do it like this, it'll start predicting like 0.5, 0.5, 0.1, 0.2 or 2. You see it, this is what it's going to do currently. Our network that we've built here will predict vectors like this. Sorry, it's my mouse is like terrible. Yeah, so it predicts vectors like this. We need to do one additional trick to force it so that it should make these 0, this a 1, and this a 0 as much as possible. We want to force it to do it. You see that? And the way that we do that is with a function called the softmax. Okay, so that's the little, if you notice, this was just exactly like your regression, but now we're also adding the softmax. And I'll do an example of the softmax in a second. So the softmax does this effect of forcing it that extra mile. All right, so let's take a look. So first, let's complete the architecture by adding softmax here. And softmax, we have to tell it to do it on dimension 1, because remember, we have batches of 64 in a tensor, or 32, Lenny said, right? So 32. So it's predicting, if we give it 32 inputs, it's going to predict 32 outputs of what size? 32 by 10. 32 by 10. Very good. Got it? So if it's 32 by 10, where do we want to apply the softmax? Not across the 32, but on the 10, right? On the 10 each vector individually, because this is the 10 that we want to force with softmax to become more like this. Okay? That's the last little bit of it. Does that make sense, guys? Yeah? All right, let's do an example of softmax. This is something that your code doesn't need. I'm only doing it more to kind of show how it works. So let's do an example. So the softmax function basically has the property that it's going to try to do that, and the numbers will add up to 1, okay? Which the numbers here do add up to 1, right? These numbers add up to 1. So the function is actually like this. We're going to use the built-in softmax, but we can define it just so that we understand how it works. So let's do my softmax. Okay. This will take a vector of size 10, right? X or 3 or whatever it is. And then we're just going to say return torch dot. And this is just the equation for it, all right? So exponential of x, and then we divide by torch dot exponential of x, but the sum of it. Dot sum. Okay? So that's the equation of softmax. What we want to look at is the behavior of it. So for instance, let's create a tensor. X equal, I'm just going to do this has to be a torch tensor for it to work. So I'm going to do torch tensor. And I'm going to give it a vector. Let's say 1.0, comma, 3.0, comma, 2.0. As you can see, this does not add up to 1. Do you guys see that? But what's important here is that this is the highest value, followed by this one, followed by that one. Do you see that? So technically, the class would be this one, the one that has the maximum value. Okay? But our data will not look like that. Our data will look like our real data, 0, comma, 1, comma, 0. Do you agree with that? Your real data will always look like this. Your regression model currently predicts kind of like this. And that's not exactly great, right? What we want is for it to be closer to this one, closer to that one. And that's why we apply the softmax. So now let's do that. So I'm going to do print my softmax X. Okay, let's go ahead, print that one, run that one. What do you think? Pretty nice, right? Pretty cool. So what did we do? If you notice, this is still maintained, right? This is still the lowest. This is still the highest, and this would be the one in the middle, sort of. But they do have one property in common. These three add up to 1. And this is just a function. I mean, somebody very smart invented this function, and this is what, by adding this, we force our model to be more like the real data, because the real data for sure looks like this. And we don't want a regression model that predicts this. We don't even want a regression model that predicts 0.4, 0.7, 0.5. We don't even want that, actually, because that still does not add up to 1. It's harder to like interpret it, is what it's saying. So you're pushing it as much as possible to be easier to distinguish, if you will. So if you look, if I try these 3 numbers, they don't add up to 1, right? But I'm going to run them through softmax. Click on it really quick. And what happened? Now it's 0.28, 0.39, and 0.31. They add up to 1. Do you see that? So it's more like the behavior here. Okay? That's it. I mean, that helps a lot in machine learning, the softmax function. To convince yourself, you can also do .sum, and you will see that this adds up to. See, it adds up to. Okay? So the softmax is the little piece that we add to classification algorithms, basically. Any questions on that one? So your classification models will need to have the softmax. There's other softmaxes that we can try, but it'll need to have it. That's your architecture for an MLP. And from here, you would be able to do other models like deep learning, etc., and so on. Okay? Let's keep going then. Let's try to finish up. So we have the data loader built. We've gone over softmax. We've created one architecture. What else do we need? We need the loss function, right? So I'm going to add some cells here. Oh, yeah. Remove this or add a comment here.
We don't have comments between the one full.
Oh, here you mean?
Yeah.
Yep. Good catch. Thank you. All right. Run. Probably just typo uppercase U. All right, there we go. Thanks, Joey. All right, now another thing that's going to change in classification is the loss function. If this was regression, what was the name of the loss function? MSE, right? Mean squared error. Oop, MSE. Right? Mean squared error, that was for regression problems. For classification problems, there's a different loss function called cross entropy. So we will do a description of these in slides at some point later. But that's going to be the name of, and basically just whenever you do classification, use cross entropy. Okay? So the cross entropy loss, just like that. And there's several versions of cross entropy. There's binary cross entropy, multi-label cross entropy, etc. Okay, guys? All right, great. So now we've defined that one too. We've got our data loader. Now let's create model FN, which is just model MLP. And I'm doing this so that in the code I can just use model FN, and then later we can change this to various different architectures. Just makes it easier. Remember, you will have to rewrite all of this in an object-oriented fashion. All right, so now let's start the training process. So we're going to do training process. And hopefully we'll be running in a sec. Markdown. Training process. Okay, so learning rate is 0.001, and epochs is going to be, let's say 100. We don't really know. We also need the optimizer, right? So we've done this before. We just invoked optim. And this time around, instead of stochastic gradient descent, we're going to use the atom. Yes. Atom optimizer. Do you guys remember this part? We've already done this in the regression. So you know how to do this. Okay. What do we provide here? The parameters, right? So model FN dot parameters. What are these? For the architecture, what are these? The weights. Remember, the weights are in here. And then the learning rate is going to be learning rate. And that's it. Good job. Right? So let's hit run. And all that's left now is the for loop for us to do this, for us to train it and see and measure performance. So for epoch in range n epochs, right? 100 times. Then we've also done this before because we've used data loaders, right? So for IMGs, comma, labels, in train What was the name of the data loader actually? Train data loader, right? Train data loader. Okay. So what do we do here? Let's first do print imgs dot shape, just because this is, and I'm going to use an input to halt it. Okay, so if I do this, 32 by 3 by 32 by 32. What does that mean? The first one is the batch size that Lenny selected. And then the images are 3 by 32 by 32, correct? So the batch size should stay as 32, but we need to spaghettify it, right? From 3 to 32 to 32 to 3072. So how do we do that? We can halt this one. Okay, let's remove this. And now I'm just going to add a comment here. Resize image, just to remind you. Okay, so images dot view batch size, comma, what? And the batch size we can just define over here, batch size equal to 32, right? Oops, sorry. That's what we had defined it to be. So add that in. All right. So what about this? -1, right? -1 will figure it out, yeah. No, just -1 here because we already saw that it's 32 by 3 by 32 by 32. So hopefully now we would have 32 by 3072. Okay. And we can verify it actually by doing the, I shouldn't have deleted the thing I deleted. 1, 2, 3, 4. Okay, I'm doing this wrong. Okay, so then this would be now print img. Oh, yeah, we need to assign this, right? So how do we do this? Imgs resized or spaghettified or something. All right, so now we do images resized dot shape, and let's add input to halt it. Everyone with me, guys? This is important, right? So it's important for you to understand what we're doing to get the architecture going. And there you go. Done. Now this will match. If we didn't do this, this would not work because it wouldn't fit into that vector. Questions? All right, so we've got that part. So now we can go ahead and finish it. I'm going to hit stop here. We resize the images. And now what do? We run the model, right? So we're going to have outputs equal model FN, right? Model FN is the architecture. So model FN, what is the input to model FN? IMGs resized. Why? Because the batch size doesn't matter, right? Eventually we could predict on one image, we can predict on 50,000 images, we can predict on the batches of 32 images. Okay? That's the input. What does outputs return? The labels, the predictions, basically. Pred. Actually, I'm going to change it to pred. Preds to indicate that there's more. And then what do we do now? You've done this before, right? Loss equal loss FN. And what does loss FN take? Preds Preds, and what else does it take? Not test. What goes here, I mean? But what is the name of the variable? Labels, right? Labels. So let's take a look at labels, actually. How about that? Print labels. Do you see what I'm doing? Let's add the input to hold it. Let's run it. Do you guys see that? So it's 32 images, but we're only looking at the labels. So it's 1, 1, 4, 7, 5, 3, 8, 1. But our model is predicting vectors of size 10. Do you guys see that? So this is a vector of size 10. This is a scalar of 1. So the one-hot encoding, remember that I talked about the one-hot encoding somewhere? Yeah, one-hot encoding is this, right? So in theory, we would have to take this number 4, for instance, got it? And convert it into this. Do you see that? And then feed it in. As it turns out, however, the functions already know that we would have to do this. And so to avoid very repetitive thing that everybody would need to do, they do it for you. Do you see what I'm saying? So you can literally just give it these values as is, and inside the function will convert them to the vector. If you had written the equations, you would have to do the conversion yourself. But because we are using a built-in function, we don't have to do it. Do you see that? But essentially, Preds is a vector of 10. Labels is just a scalar. And I'm excluding the batch here for simplicity. It would really be 32 by 10, 32 by 1. If you don't believe me, simple. We go to the description of the function where it describes to you, where it describes to you how it works. But what's important is that you should understand that really the label needs to be one-hot encoded because it predicts a vector of size 10. This is how it is. It's just the function helps you out and doesn't require you to explicitly do it. It'll do it. Make sense? Okay. Now we can look up the function. So that would be NN cross entropy, right? So NN dot cross entropy. Looking these things up is it's recommended. So I'm looking for it. Trying to see if I find that definition. Yeah, so I mean, I'll go to the function. So it would be NN dot cross entropy loss. Okay, so you can click on this one. And it provides here the whole definition, basically, of the function. Okay. So you can read through this, basically, but it should specify in there that it's doing. Got it? All right, so I leave that kind of to you. So we don't have to directly make the change. Input shape. Right, so it'll do the computation. All right, so let's try it out. Let's go back to the Jupyter notebook. Hit save here. I'm going to change that. Okay. So now let's do this, that. Why is this running? Not sure why this is running here. Shouldn't, right? It should not be doing that. Let me stop this. Okay, so this is fine. Yeah, I don't know why I did that. Okay, anyway. So let's go to this part. Okay. So we have we can comment this out. We predict the preds, we do the loss function calculation. And then what else do we usually do after that? Once we have the losses, which is the predicted versus the real, we do what? We invoke optimizer, zero out the grad, loss backward optimizer dot step. Those same three commands that we had done before. So I'm going to do optimizer dot zero grad. So as you can see, it's very similar to what we did before. Then we do loss dot backward. And finally, we do optimizer dot step. Same idea. Calculating the derivatives, determining if the weight should be plus or minus, and then taking the step to update the weights. And then that's it. Let's just go ahead and print for every epoch the loss. And what should we expect if everything worked? We should expect the loss value to go down, correct? In a perfect world. So let's go ahead and run this one. No errors so far. But we should start seeing loss values. So I'm not seeing. Yeah. Are any of you seeing loss values being printed out?
Did we not do like the modulus?
It might be outside of, it might be where you place.
It just took a minute for mine.
It took a minute,
Yeah.
but is it printing losses now?
Yep.
Oh, okay. All right. That's kind of what I wanted. Mine is just losses. So it's printing losses for some of you?
Yep.
Okay, perfect. Is the loss going down?
I haven't gotten the second.
Really? Okay. Okay. So what's the problem? Too big.
Maybe, yeah, it's a large batch size.
It's too big. So what do we do?
It's going down though.
But how many epochs have you got? 2, right? Out of 100. So it's very slow. Welcome yet again to deep learning, right? It's gonna tax your computers quite a bit. So what can we do to speed this up? My suggestion would be to change the architecture to fewer weights. Do you see that? So I'm going to, I just got one. Okay, no, I didn't. Still have them. All right, so I'm gonna kill this. And I'm gonna change the architecture to 100. Why, or even like 60. Why? Because I want it to run faster. However, keep in mind, whoever has the GPU and keeps it at 510 may win the competition. You see that? Because that's how it works. Got it? All right, so let's try it with 60. So change the architecture, run everything again. Let's hope this is faster. Doesn't seem to be faster. So what else can we do? You got an error?
Yeah, the dimensions are multiplying.
Really?
Things are going by a lot faster for me now,
Okay.
like about 5 seconds.
Mat 1 and Mat 2 shapes cannot be multiplied. You guys are getting this?
Yeah.
Okay. 30. Huh. That shouldn't be an issue. I know why. No, I don't know.
Why did it print and then error? Mine printed and then error.
I don't know why I'm getting an error here, actually. We reached the batch. This is 30. This is 372. Duplicate shapes cannot be multiplied. You know what? I think it might be that this model is like mixing the new and the old. Just refresh the.
I mean, mine, it gave me that error on the first run.
You had never run it before?
The only difference I saw between my code and yours
Uh-huh.
was I didn't use the variable batch size in the images view. I just directly pulled from the images that.
Yeah. I know what you mean, but it's 32. I see what you're saying, yeah.
Plus the refresh works for you.
Yeah, I'm thinking maybe it just got mixed up. Because this has nothing, this change that I did would not affect it. Did you find it, Joey, what the issue is?
It goes through a few of them. And I think a certain image failed.
A certain image?
Yeah,
That's odd because,
because it's I like do a print and it's like, it's getting a lot of them, but then one of them fails later on. That's why some people are fine because it's like.
it's that,
Oh, one of the images is of a different size.
Yeah.
Yeah, that's why, because I was confused, because it's keep going out 1536, and I'm like, where is that coming from? I think that's the size of one of the images.
that's, yeah. But that's odd though,
Yeah.
it's really odd. It's running, so let's see what happens here. I did refresh it. Yeah, go ahead.
Do you know off the top of your head a way to, like, where it's printing the loss?
Yeah.
Also print like how much of your memory is starting to get.
Yeah, I don't know where that would be.
I'll
I
have
mean,
to look that one up.
I'm sure there might be something, but I don't know the command. This is an odd error.
Randomized, I bet if you did a different batch, it would be fine.
Joey, so have you gotten losses?
No, I can't do the first batch. Image, I mean, the image with the index 1562 is in the top side. Trying to out print again.
Okay, so it's very big.
Oh, yeah. The image is 16 by 3 by 30 by, wait, that's at the back side.
Is your computer just on that?
32.
Without it.
Huh.
No, the. Oh, that's. Now it's 61.
You're on your computer.
Yeah.